I'm really going to be very focused on cancer and the translation aspect of these genetic aberrations. So these are the changes that we see in the somatic genome, that is in the cancer genome, and not in the germline DNA of cancers. And they can be broken down into different categories: copy number changes, amplification of HER2, for example, or homozygous deletion of a tumor suppressor gene, mutations, and that can be either changing the composition of the DNA or a protein, or actually leading to a stop codon, so prematurely ending the transcription of a particular protein. So some of these important substitution includes BRAF mutation, IDH mutation, or P53 mutation. There are a lot of these, and we profile many of these in POG. Something that is analogous to mutation are insertion deletions, or indels. These are very small addition or deletion of base pairs into the cancer genome. And they can result in significant biological changes to the cancer cells. For example, in non-small cell lung cancer, insertion deletion events in EGFR can lead to aggressive growth and independent of EGF ligand. At the same time, cancer cells with this particular signature are susceptible to tyrosine kinase inhibitor. So you can see why it's so important to identify these changes and say, okay, with this patient, with this particular change, he or she will benefit from this particular therapy. I think something that's really coming up really rapidly in the past 5 or 6 years is the identification of rearrangements or gene translocations, not only in hematolymphoid organism and sarcoma, which has been traditionally associated with this type of changes, but finding these changes in epithelial neoplasms, adenocarcinoma, even brain tumors, we're finding a lot of these translocation events in which we're bringing one gene together with another gene that are typically not together. And by doing that, you can actually ramp up the activation or the activity of the other gene. And this has proven to be something that whole genome sequencing and transcriptional sequencing is really good for uncovering. Three billion base pair only codes for 22,000 genes. And those 22,000 genes, the information is only 1.5% of the genome. So this is really the basis of exome sequencing, in which we really reduce information that we seek and focusing on the part of the DNA that codes for the protein. And the next reduction of that really is amplicon sequencing, which is panel sequencing. So essentially, is asking information particularly about, okay, I know that there are 5 gene hotspot regions that are implicated in cancer treatment. BRAF mutation, codon 600, KRAS, codon 12 and 13, maybe 61, IDH, for example, P53, PIK3CA. Maybe you have a clinical trial for PIK3CA, and you want to identify the mutation that leads to activation of the protein. So you need to develop a panel a priori. So you have to have some sort of knowledge saying that, okay, I want to cover these particular regions. And by doing that, you can have a really focused test. Obviously, this theoretically will allow you to have a quick turnaround, very focused result, so that you don't get bogged down by all the bioinformatic calculations of the 3 billion base pair of whole genome sequencing. How do we integrate and use RNA sequencing data? And I think this is really one of the key difference between Genome Science Center, the POC approach with other places, is that we actually we made this decision a long time ago to integrate RNA-seq data with whole genome sequencing data. It does come with some challenges in that we do need to get quality sample to make RNA library. But I think at the other end of it, the result of RNA sequencing has been extremely useful for making clinical decisions or informing on potential pathway on patients. So obviously, RNA sequencing will corroborate findings from DNA. Do we see this mutation in RNA or not? And it gives us information on exon usage and splice variant, which we know could be an important oncogenic event in cancer. But I think the most important information it gives us is that it gives us information on which pathway is activated. Does this cancer have activated MAPK pathway, EGFR pathway? Could we target that pathway? Does mutation in this gene activate this pathway? This is really what we are using RNA sequencing data for.